So we're going to talk about molarity in this section. I'm going to focus mainly on the math of it. Molarity by definition is an amount of solute in moles over the volume of the solution in liters. We can use molarity as a definition, an algebraic equation, and a conversion factor. Okay, so molarity is just another unit you're going to learn that relates directly moles and volume. So in this particular example, it's asking you to dissolve 25.5 grams of potassium bromide in enough water to make a 1.75 liter solution. What is the molarity? Well, what we know is that, excuse me, you are given the mass of the potassium bromide and the volume of a solution. Remember, molarity is moles per volume. So we do not have moles. Moles was not given here, but we were given the grams and we know the volume. So that's what we were given, and we have to find molarity. So we have to first find the number of moles present in the 25.5 grams of KBr. That's our first step. We can't do anything until we're in moles. So what we're going to do first is convert grams of potassium bromide to moles using potassium bromide's molar mass, which is given to us in this problem, but you can easily just go to a periodic table, add together a potassium and a bromide, and you get the molar mass. And then we're going to use the moles that we find and the liters that were given to find molarity. This is our plan. So first, here's the conversion of grams of potassium bromide to moles. And so we're simply just going to divide the grams by the molar mass. Here is our molar mass. And this gives us our moles. Our second step is going to be to take the moles that we just found, plug them in, and use the liters that were given to solve for molarity. So we have 0.21429 moles divided by 1.75 liters of solution. That will give us a molarity of 0.122 capital M. Now, a couple of things I want to talk about. When we get this answer right here, what we can say is that we have a 0.122 molar solution of potassium bromide. Okay, that's going to become important. When you see that 0.122 capital M, that is the concentration. Molarity is the concentration. You're also going to need to get in the habit of taking this and thinking about it in terms of this. Okay, that's because when we use molarity as a conversion factor, this is the format in which we need it. If you use just this or this, you will confuse yourself when it comes to the math. Okay, so always stick to this format when we do what we're going to call solution stoichiometry. That's using molarity in a word problem to get from volume or molarity of one thing to volume or molarity of another thing. So here's another example. It says to calculate the molarity of a solution by adding 45.4 grams of sodium nitrate to a flask and then dissolving it with water to create a total volume of 2.5 liters. So our first step here is going to convert again the grams of sodium nitrate to moles of sodium nitrate, and we're going to do that using molar mass. And then we're just going to divide the moles by the volume. Same setup. So here we have the grams converted to moles. I simply took the molar mass of sodium nitrate and I divided it into the grams that were given. And then we're going to take those moles and just plug them in to there and use the volume given to find the final molarity. So like I said, molarity can be used as a conversion factor between moles of the solute and liters of the solution. So an example here is a 0.500 molar sodium chloride solution contains 0.5 moles of sodium chloride for every 1 liter of solution. That's literally what we're saying when we say 0.5 molar sodium chloride solution. We're saying it's 0.500 moles of sodium chloride, the solute, for every 1 liter of solution. By using molarity in this format, remember I started a few slides ago, we can easily convert between liters and moles of what we're dealing with. So for example, how many liters of a 0.125 molar sodium hydroxide solution contains 0.255 moles of sodium hydroxide? Well, we are given the concentration. Molarity is concentration. And we know how many moles there are of the sodium hydroxide. The question is, how many liters would that be? So our plan is to convert moles of sodium hydroxide to liters of solution by way of the molarity as a conversion factor. This will be our unit factor. So we're going to always follow the same thing. Our given times our unit factor or factors will equal our unknown or our asked for. So our given is the 0.255 moles, and we know we start with that because if we start with the molarity, we can't really do anything with it. Okay, so starting with that means I can easily and simply take my moles that were given and use the molarity as a unit factor, making sure moles cancel. Because what I did is I took that 0.125 molar and I turned it into 0.0125 moles of NaOH for every 1 liter of solution. Okay? So what this means is every 2.04 liters of a solution that is 1.125 molar will have 0.255 moles of sodium hydroxide contained in it. So when we talk about preparing these solutions, how can we prepare these? Well, we have to think about what's really going on. We're going to take our solid, our solid, whatever it is, in this case, sodium chloride. If we wanted to make a 1 molar solution of sodium chloride, that's 1 liter, we would take our 1.00 moles of sodium chloride, which is 58.44 grams, and we'd add it to our flask here, the solid form, and then we fill with enough water so that the water is filled to the 1 liter mark. Okay, so 1 mole would be weighed out, which is 58.44 grams. We're going to add water to the 1 liter mark here. Okay, that's 1 liter. This is a 1 liter flask. And then we will have it all mixed together. Okay, so solid, weighed out first, water added to the 1 liter line because that's what it asked for, and then it's mixed together. And that is a 1.00 molar solution of sodium chloride. Now, this is very different than dilution. Dilution is taking something that is highly concentrated and using a little bit of it, adding it to water, or adding water to it to make it a lower concentration. We actually use terms in our everyday world that are completely wrong. When we say, oh man, this coffee is really, really strong, what we mean is it's highly concentrated. Or if we say, oh, this iced tea, it's really watery. It's not really, it's really weak. What we're saying is it's too diluted. okay? If you've ever used powdered drinks to make like a pitcher of, say, lemonade or iced tea or something like that, what you do is you take a little bit of the powder and you follow the directions on the container, and it'll say 3 scoops for every 2 cups of water or something like that. Well, if you don't use enough powder, it's going to be a very weak, watery tasting drink. If you use too much powder, it's going to be very strong and very highly concentrated. If you make it too concentrated, what can we do to fix that? We can add more water to dilute it. So the idea is dilution is not a relationship between 2 different things in a chemical reaction. Dilution is simply taking something that's highly concentrated and making it less concentrated. The mathematical relationship we use is C1V1 equals C2V2, where C is concentration, and we know molarity is concentration. So we can simply say M1V1 equals M2V2. Now, when we do this, we are simply saying, well, what if I have a 10 molar stock solution of calcium chloride, and I want to make a 0.5 molar concentration 3-liter solution? How do I do this? Well, if I use M1V1 equals M2V2, then I can simply say, okay, I know the molarity of the highly concentrated stuff, okay? Here's the molarity of the highly concentrated stuff. That's typically your M1. The stuff on the left-hand side is often your highly concentrated side, and the stuff on the right-hand side is your weaker concentrated or diluted side. All right. Now, we have our highly concentrated stock solution. We also have our, we know how much volume of the diluted amount that we wanted. We know we wanted a molarity of 0.5 and a volume of 3 liters. So the question is, how much of the highly concentrated stuff do we need? We know that. So how much of this do we need? Well, if we solve for x, we're going to find that it's 0.150 liters. Okay? We simply took M1V1 equals M2V2, and we said, okay, you know what? We know what M1 is. M1 is the new concentration, 0.500 molar. We also knew that we needed 3 liters of that. We had no idea how much of the highly concentrated amount to use, but we did know that it was 10 molar. All right, so if we just solve for x, or in this case, V1, we are going to get that set up, and we're going to have 0.5 times 3 divided by 10, and we get 0.150. Liters, okay, or 150 milliliters. Okay, so what does this mean big picture? What this means is, in order to make this solution, I would have to add here 150 milliliters of the highly concentrated 10 molar stock solution into my flask. Then I would fill with water up to the 3 liter line. Okay, so then it would be all mixed together and it would dilute this highly concentrated amount. So, to what volume should you dilute 0.200 liters of a 15 molar sodium hydroxide solution to obtain 3 molar sodium hydroxide solution? Well, we know our initial volume and our initial molarity, and we know the molarity we want. What we don't know is the volume of that. So how much of the higher concentrated molarity solution should we use in order to get a 0.2 liter 15 molar sodium hydroxide solution? I totally said that backwards, but I think you know what I mean. All right, so how much volume are we going to actually get? Sorry, completely said it backwards. How much volume are we going to get by diluting this? Well, we're simply going to use M1V1 equals M2V2. We know everything but this. So we can simply plug and chug and then solve for X. By the way, it doesn't matter if you solve for your unknown first and then plug the numbers in, or plug the numbers in and then solve for your unknown. And it also doesn't really matter which one you identify as the M1V1 and M2V2, so long as the correct molarity and volume are together. So for example, I wouldn't want you to use M2, which is 3 molar, with V1, which is 0.2 liters. Okay, you got to keep the right things together. And the trick about doing that is saying, okay, what do I got going on? I got 0.2 liters of something. All right, so those go together. So when you solve for V2, you get M1 times V1 over M2. Plug and chug your numbers, making sure to keep these together, because they go together, as your M1 V1, and then plug and chug and solve, and you get 1.00 liters of solution. So what this translates into is I would need a total of a 1 liter solution in order to get my 3 molar concentration. So what this means is if I had my flask and I added to it 0.200 liters of 15 molar solution, the next thing I would do is I would fill up with water to the 1 liter mark, so that when all was said and done, I had a 3 molar solution. Now, sometimes it's going to look like you can use M1V1 equals M2V2, but you absolutely can't. You know you can use M1V1 equals M2V2 because it either says dilution or highly concentrated or lower concentrated solution, and you're only dealing with one entity. You need to actually use solution stoichiometry or molarity and balanced chemical equations as unit factors instead of the dilution equation when you have more than one thing that they're talking about. Okay. Now this first example, it's a little bit more difficult because I've not only made this a solution stoichiometry problem, but it's also a limiting reactant problem. So we're going to talk about both. The problem states how many grams of silver chromate will precipitate when 150 mils of a 0.5 molar silver nitrate solution are added to 100 mils of a 0.4 molar potassium chromate. Now, just like limiting reactants before, when you were given the grams of 2 reactants, that was your clue that it was a limiting reactant problem. In this case, you're not given grams, you're giving volume and molarity of each reactant. So you have to treat it as a limiting reactant problem in addition to a solution stoichiometry. So with solution stoichiometry, what we're going to look at here is first the balanced chemical reaction that I've already given to you. It won't always be given, and if it is given, it won't always be balanced. So always double check. Now, we know that I have a 0.400 molar, I copied the wrong one, sorry guys. I have a 0.500 molar solution, and I have 150 milliliters of it. So I'm just going to go ahead and automatically make that a liter because I need liters. You cannot use milliliters with molarity. You need to convert your milliliters to liters. And I also have a 0.4 molar solution of a 0.1 liter potassium chromate. Okay, that's my given information. So the question is, how much silver chromate will actually precipitate out? So what I'm going to do is I'm going to take each reactant, its molarity and its volume, and convert it to the product. I'm going to do that separately in 2 different steps. And just like limiting reactants, the one that gives me the least amount of product is my limiting reactant, and also the amount of product I will get. So the first thing I do is I take my given volume of silver nitrate, and I use the molarity as a conversion factor. Remember, immediately when you see a volume and a molarity, take that molarity and put it into the moles per liter format, the one that I starred. That way you're sure to get everything to cross out and cancel out correctly. Okay? By doing this and multiplying the liters by the molarity in the form of moles per liter, that will give me moles of silver nitrate. Then I'm going to use the coefficients from my balanced chemical equation. Those are the coefficients from my balanced chemical equation to convert between silver nitrate and silver chromate. Then I'm finally just going to find the molar mass of silver chromate. This is the molar mass of silver chromate, and I will just add together 2 silvers, a chromate, and 4 oxygen to see what my gram weight will be. My moles of silver nitrate cancel, my moles of silver chromate cancel, and I'm left with grams. Okay, now this one will give me 12.4 grams of silver chromate. Now I'm going to do the exact same thing with the potassium chromate. Okay, I'm going to say, okay, here's my volume. And then I'm going to use my molarity as my conversion factor to get to moles. This way, liters cancels out, and I got moles. Then I'm going to use the coefficients from the balanced chemical equation to go from moles of potassium chromate to moles of silver chromate. And then finally, I'm going to use the molar mass of silver chromate to get the grams of the silver chromate. And what I have found in this particular example is that going from volume to moles using molarity, then moles to moles using the coefficients from the balanced chemical equation, then going to grams using the molar mass. That is my setup. And what I can see here is that the silver nitrate is the limiting reactant, and it will give me 12.4 grams of silver chromate. Here's another example. I made this one a little bit more simple. What volume of 0.415 molar silver nitrate will be required to precipitate as a silver bromide all I don't know what I just wrote in here. I must have missed a word. I'm sorry, guys. As silver bromide, all the bromide ions in 35 mils of 0.128 molar calcium bromide. I'm sorry, I had a typo here somewhere. So let's just go through this. I have silver nitrate, and I was told the silver nitrate is 0.415 molar. And I have calcium bromide, that's 35 milliliters, and it's 0.128 molar. The question is, what volume of silver nitrate will get me this precipitation? That's what this question is supposed to be asking. Okay, so we have 0.415 molar AgNO3 and 35.0 mils of 0.128 molar calcium bromide. The question is, where do we start? We start in the only place we can, where we're given two pieces of information that will get us to moles. Once we're in moles, we can use our balanced chemical equation to flip-flop between different things within that chemical equation. So the only place I can start is right here. I'm going to take my volume of the calcium bromide and use the molarity to get to moles. So I've gone from volume to moles using molarity. Then I'm going to convert to moles of what's being asked for, which is the silver nitrate, using the coefficients from the balanced chemical equation. Okay? Then I'm going to get to liters by way of using the given molarity. We were given this molarity, which we're going to think about in terms of 0.415 moles per 1 liter. And I'm going to use that as a conversion factor so that liters canceled, moles canceled. Now moles have canceled again, and I'm left with liters, which is what it's asking me for, volume. So I multiply the whole top together, divided by the whole bottom multiplied together, and I find that I need 0.0216 liters of silver nitrate. That is 0.415 molar to get all of this to react. Okay? And that's solution stoichiometry. You cannot use M1V1 equals M2V2 with this problem. Any of these problems. When there's two different things involved, do not use M1V1 equals M2V2. It will not always work, and often it will not work. So once in a blue moon, it might happen to work out, and it's just happens to mathematically work out, but generally speaking, it doesn't. So the rule is, if you have one thing with two different concentrations and different volumes, but it's one thing, use M1V1 equals M2V2. If it's two different things with volumes and molarities, use solution stoichiometry, the actual longhand math of conversion. Here's another example. I will upload this PowerPoint for you to go through the examples that are there. It's different than your book's PowerPoint. This is from a different book I use. Same stuff, just a different book. So you can go all through these and look at them in more depth. I've also put solution stoichiometry problems worksheets up for you to practice with. That's all we're going to do on this topic. If you have any questions, feel free to email me. And we will hit the next lecture. I'm going to talk more math stuff. A lot of this is very math heavy. So just kind of keep that in mind. A lot of these lectures are going to focus just on the math because it's very math heavy, and you really need to be responsible for going through the PowerPoints and the definitions and using your book and all those tools, and then use these lectures to see the math behind it worked out and explained. If you have any questions, feel free to shoot me an email.